Today's warm-up question is going to lead us into the notes that we're starting today over Newton's second law, and it's also kind of a follow-up on the RA that you guys did yesterday. It says, if you push two objects with the same force, which do you expect to move faster after the initial push? You have two options, A or B. A is a box full of books, B is an empty box. Which one do you think would move faster after you pushed it? B. You saw the same thing yesterday. The cart that didn't have any masses in it should have been moving faster than the one that did. Okay, and that is we're gonna look at today the relationship between the mass and acceleration of an object, which is part of our discussion in Newton's second law. So we're going to get into this as well today, but please go ahead and answer the warm-up question. It is answer choice B, and then there's also a kind of check-in underneath it on My Open Math for you to put in there kind of how you feel about the stuff we've talked about so far, or if there's any particular areas or things that you would like or think that you're struggling with still. So again, just for you to think about on your own, but also fill it in there. You do have homework tonight. However, if we finish these notes as quickly as we did in my other class, you're going to have about 20 minutes left, so you should be able to finish it in the room. But if not, then it will be homework due by 11:59 p.m. tonight. And then as a reminder, you also have the fan cart RA, but it's not due till next week, and we do have a work day next week as well, so you don't have to do that at home. It's completely up to you if you want to work on it, but you will have some more time for that in class next week. All right, following up on the warm-up question, an object will accelerate when a net force is applied to it. Okay, its acceleration or force or mass, any of those three variables, can be calculated using the equation F net equals ma, which is referred to as Newton's second law. Newton's second law describes or tells us that the acceleration of an object depends on two variables, the force that's acting on that object and the mass of the object. And those are the two things that you tested in the RA. You tested changing the force of the fan to see how it affected acceleration, and you tested changing the mass of the cart to see how it affected acceleration. And so you should have an idea of these things already, but again, specifically this equation tells us that acceleration is inversely proportional to mass, but directly proportional to net force. So that should be what you saw in your data as well. So again, acceleration is inversely proportional to mass, but acceleration is directly proportional to net force. So again, we're going to look at this more in depth today, but you have already seen these relationships, at least touched on them, in the RA from yesterday. And this is Newton's second law. Now, Newton's second law obviously refers to force, and we haven't actually talked about forces yet. So let's go ahead and define what is a force. A force is a vector quantity that describes a push or a pull on an object due to an interaction between two or more objects. And again, we can calculate what that force is if we know the mass of the object and its acceleration. We'll look at more equations later on that involve force, but for now, this is the only new one that we have, and so it's the one, or the only one right now that you can use to solve for force. However, I do want you to be aware of the units when you're using this equation. Just like any other equation, you have to check those units. For Newton's second law, for this calculation to work, your masses need to be in kilograms. So if you read a question and it tells you that a baseball has a mass of 435 grams, that means you're going to have to do a conversion to kilograms. Similarly, your accelerations have to be in units of meters per second squared, or that's the same thing as meters per second. But if it's in any other unit, centimeters per second squared, something like that, then you'll have to do a conversion for that as well. When you multiply a mass in kilograms by an acceleration in meters per second squared, it gives you a force in a unit called a Newton. Newtons is abbreviated as a capital N. And that's what's on the screen, and that is our unit for force. If you're not using kilograms, you're not going to have a Newton. Okay, and similarly, if you have Newtons and you're trying to solve for a mass, you're going to be solving for that mass in kilograms, because that's the unit you get when you're using a Newton. A Newton is the same thing as a kilogram meter per second squared. So it does cancel out if you write it out fully, but we shorten it to newtons because that's a lot easier and less confusing to look at than kilograms times meters per second squared. But it is the same thing. All right, so again, force, push or a pull. That's the most basic definition of a force, is a push or a pull. And you probably would have said that if I asked you to define it yourself or something similar to that, because you guys have an idea of what a force is. Now, there are different types of forces, and we will go more in depth into these later on. We're not really focused so much on the types of forces in this unit, but I do want you to be aware of them, and so I went ahead and included them in today's notes. There are two main types of forces, contact forces and field forces. Contact forces are going to be any force that an object experiences due to an interaction where the objects are touching. If they're in contact with one another, it's a contact force. On the other hand, if they're not actually touching and the force acts at a distance, we call those field forces. For example, you can feel, or like the moon feels the gravitational pull from the Earth, and yet it's not touching the Earth. And so it's due to Earth's gravitational field and the overlap of their two fields. So again, field forces are going to be things like gravitational force or electromagnetic force. Maybe you have played with magnets and you have seen magnets repel at a distance before. And then the other two that are up there, strong and weak nuclear force, those are not forces we talk about in this class other than to say they exist and that they are field forces. So we're not going to go into those at all. Contact forces, on the other hand, we're going to use a lot. Applied force is going to be any force that is applied by typically a person. In the question, it'll say, Sarah pushes a box with 12 newtons of force. That would be an applied force. We're not going to focus on normal force just yet. We will talk about it in the next unit a lot. Friction is one that you're probably already familiar with. That's a force due to surfaces that are rubbing across one another as one slides over the other or rolls over the other. Tension is going to be force in a rope or maybe a cable, string, something like that. Spring force is, of course, a force that a spring exerts, or it could be some other type of elastic object. Air resistance, which is also known as drag force, and then buoyant force. Now, we don't really talk about fluids or buoyancy in this course, but I went ahead and put it up here because it is a type of force. So again, we'll talk more about these later on. I just wanted to show you some of the forces that you will see as we talk about forces throughout the year. So let's look at an example calculation for Newton's second law. This one, again, it's a good one to copy down if you want an example, but it says Sandy uses positive 48 newtons of force to move a 23 kilogram sofa. What is the acceleration of the sofa? Again, we're going to go through the same problem-solving process that we've done previously. We're going to label all of our givens, and so far there are only two numbers in the question. The first is the force of positive 48 newtons, and the second is the mass of the sofa, 23 kilograms. The unknown that we're being asked to find is acceleration, and the equation for this is F equals ma. That's the Newton's second law equation that we just took down in our notes. Your next step is to substitute into the equation. However, before you do that, please double check your units. We already have newtons and kilograms. Those are the units we want, so there's nothing that we need to convert, but double check first, because if you don't, you might make a math mistake. That's going to be 48 equals 23a. Again, if I want to solve for a, I need it by itself, which means I need to divide both sides by 23 so that cancels, leaving a equals 48 divided by 23. And when you type that into your calculator, you get an acceleration of 2.09 meters per second, and it is a positive acceleration, and the reason is the force was a positive force. The acceleration that an object experiences will be in the same direction as that force. Okay, because the force was in the positive direction, the acceleration will be also. All right, so again, pretty straightforward calculation. I think you guys will agree that's easier than using those kinematic equations. It's just three variables. Okay, now the tricky part comes not today, but later on when we start combining the two together. Because obviously acceleration is the common thread in these two equations. Acceleration is in our kinematic equations and in this equation. So it's coming. We're going to start including both of them together, but not today. But let's ask this follow-up question. If half the force was applied to the sofa, how would its acceleration compare? If you pushed it half as hard, or rather if Sandy pushed it half as hard, would you expect the acceleration to be the same? No. Would you expect it to accelerate more or less? Less. Okay, and if you're not sure, check it. I just changed the force here to half as much. It was 48, now it says 24. We can redo the math. When it was 48 newtons, the acceleration was 2.09. Let's see what it is when we have half the force. Again, it's the same exact thing. We're just plugging in a different number. 24 equals 23a. Solve for a. 24 over 23 is 1.04. Notice the acceleration is half as much, which is what you guys probably predicted that it would be, given the relationship that we've already talked about that exists between force and acceleration. Force is directly proportional to acceleration. If you have half the force, you will get half the acceleration. If you have 3 times the force, you will get 3 times the acceleration. And if you're not sure, redo the math and see. You can prove it mathematically if you don't understand the relationship or don't remember what it is. Okay, I got 1.04. That is half as much as I had a moment ago. All right, so that's questions about this one. All right, let's do another example. This one says, Alex pushes a 12 kilogram shopping cart with positive 27 newtons of force. What is the acceleration of the cart? Very similar problem to the last one, different numbers, but otherwise the exact same process. We know the mass, we know the force, we know that we're looking for acceleration. We're still using F equals ma. When we substitute in, it looks like this. Again, check your units. These are good. Kilograms, newtons, we're good. 27 equals 12 times a. If I want a by itself, I need to divide both sides by 12. When I do that, I have 27 divided by 12, which is 2.25 meters per second squared. I have the positive sign there because your acceleration is always in the direction of your force. My force is positive, therefore my acceleration is also positive. Again, same thing. Follow-up question. If the cart had half the mass, how would its acceleration compare? This is pretty much what our warm-up question was like. Okay, you had a box full of books and an empty one, and I said, which one would you expect to move faster? And you said the empty one. Same thing here. If I have half as much mass, I should expect it to accelerate more. We've already talked about that relationship, but let's go ahead and check it. Instead of 12, let's try 6, half the mass. Okay, redo the problem with half the mass. 27 equals 6a, 27 divided by 6, and you get twice the acceleration. Okay, so when you have half the mass, you double your acceleration. That is an inversely proportional relationship. Again, you already took notes on this. Force is directly proportional to acceleration. Mass is inversely proportional to acceleration. Hopefully you wrote down those bullet points, but if not, write them down now or write down these examples. Does anybody have a question about this one? I've got one more. Let's do one more example. A boy pulls his 170-gram stuffed bear with a force of negative 0.88 newtons. What is the acceleration of the stuffed bear? Again, label things. I have a mass, 170 grams. I have a force, negative 0.88 newtons. Force is a vector. Pay attention to that negative sign. I'm looking for acceleration again. Okay, and so I'm using F equals ma again. And when we substitute in, we'll plug into that. However, before we substitute in, check your units. This time, we have a problem. You cannot substitute that in as it is. That's in grams. Before you do this next step, you have to convert it to kilograms. If you don't remember that conversion factor, write it down in your notes right now. There are 1,000 grams in a kilogram. Okay, it takes 1,000 grams to get a kilogram. So if I only have 170 grams, that is a small fraction of a kilogram. In fact, specifically, it's 0.170 kilograms. Divide it by 1,000. That's how I got that. Okay, so 0.17. That's the number that goes in when you substitute. So my force is negative 0.88. It is equal to my mass, 0.17 times A. From here, the math is the same. I just wanted to give you one with a conversion in it so that you know to check. All right, so when I divide both sides by 0.17, that's what goes in my calculator, negative 0.88 divided by 0.17, and my acceleration is negative 5.18 meters per second squared. It's negative because my force was in the negative direction, and my acceleration will also be in the same direction as my force. Questions about this one? Follow-up question, one more. If the boy's sister pulls with a force of 0.88 newtons in the opposite direction, what do you think would happen? Is the bear still going to accelerate at negative 5.18 meters per second squared? No. If they're pulling in opposite directions, think of a tug of war, and they're pulling with the same exact amount of strength, it's going to look like this if you were to draw a diagram. By the way, I would recommend that you draw a diagram. If a question describes more than one force, draw a picture so that you can see the forces. These pictures have a name. Okay, we're going to talk about what this diagram is called in a moment. But when you draw that picture and you label it, guys, what's the total force acting on this bear? It ends up being 0 because they cancel each other out. Okay, so you end up with a net force, that's the term for the total force, of 0. We're going to define net force in a second. And if you have 0 net force, it's like a stalemate. It's not going to go anywhere. If you're pulling exactly as hard as somebody else in opposite directions, you're not going to move because the forces cancel each other out. Net force, okay, that's the term. I want you to copy it down. The net force is the sum of the forces acting on the object. When you have more than one force acting on the object, you want to calculate that total force, also known as the net force. Because forces are vectors, direction matters. So when I say it's the sum of the forces, negative 0.88 plus positive 0.88 is how they end up canceling out. Opposite forces will cancel out completely if they're of equal magnitude, just like the bear in the previous problem. They're not always exactly the same magnitude. Maybe one of the forces is positive 5 and the other one's negative 3. Well, then they'll cancel out partially. Okay, in that case, if you had positive 5, negative 3, you'd end up with positive 2 as your net force. But it is the sum total of the forces when you take into account their direction as well. So you need to make sure to include a negative if they are backwards. If the forces are in the same direction, you will add them together. Okay, but that is how you're going to come up with your net force, is the sum total of all the forces that are acting on the object. Sometimes that means you subtract. Sometimes that means you add. It depends on whether they're in the same direction or in opposite directions. But you're going to see net force come up over and over and over again. All right, and I told you that picture, that diagram had a name too. If you have more than one force, draw that diagram so that you can figure out your net force more easily. That diagram is called a free body diagram, which I will abbreviate FBD. I don't like to write out the whole thing, free body diagram, it's long. So you'll see FBD quite a few times in questions. It'll say, draw the FBD for this. Okay, an FBD, or free body diagram, is a tool that we use to visualize the forces acting on a system or object. They show the relative magnitude and direction of all of the forces that are acting on that object. When we show the object, we don't draw a picture of the object. Don't draw a bear. Draw a box or a circle or a dot, okay? And you can label it bear if you want. That's what I did in my example. But you're not going to draw a picture here. It's just a representation. Pick a circle or a square and then draw your forces from that square. All the forces that act on the system are shown as arrows, and we draw those arrows so they point away from the system. Okay, so the arrows always start at the box and then move away from it, either to the left or the right, or up or down, or sometimes at an angle. We'll deal with that later. The arrows can be labeled with the numerical value for the force. If they tell you, hey, this is 0.88 newtons, you can label it 0.88 newtons. Or sometimes they don't give you a number value. You can just label the type of force from that list of forces that we had earlier. Like maybe it's an applied force and they don't tell you how much it is. You could label it F, or force applied, or just write applied on it. There's symbols for it too. We'll talk about those later. All right. So again, free body diagram is going to be a useful tool. You will see these throughout the year, not just this unit, but in other units throughout the year. Here are some examples of free body diagrams, and I have a question up here for you to answer. If you're wanting to copy down some examples, these might be helpful ones for you to look back at. It says, what are you able to tell me about the net force acting on each object for the following? So when I look at this first diagram, for example, what can you tell me about the net force for this upper left-hand diagram? What is my net force? What do y'all think? Look at the diagram up there. There's 20 and 20. One to the left, one to the right. What's my net force? Zero. It's just like the bear. If you have forces that are equal and opposite, they will give you a net force of 0. They will cancel each other out. Okay, what about the one underneath it? This one that says 7 and 20. What can you tell me about the net force there? 13 newtons. Which way? To the right. Okay, include a direction. Okay, so that one has a net force of 13 newtons to the right. That's all we're doing when I'm finding net force. The other two don't have numbers on them, so I can't give you a number value, but I can tell you what direction the net force is in. For this one that says tension on it, the net force has to be to the left. There's only one force on that one. Okay, what about the one underneath that? Those hash marks that you see on my vectors here, you should recognize those from your math class. Geometry, I think specifically, you use those on triangles and stuff. But those are shown, those marks are used to show that things are congruent. And so if you see those, even though there's not numbers on them, I know that those two forces are equal to each other in magnitude. They're opposite in direction. So if they're equal and opposite, then I know that they cancel out, and that's another example of 0 Newton net force. Okay, so even without numbers, I can tell you that one is 0 newtons. So you should be able to look at a diagram and tell me about the net force. Either tell me which direction the net force is in, or give me a numerical value if you have numbers to work with. All right, so again, let's go to another vocabulary term. I've highlighted 2 of these diagrams in green. And I highlighted these 2 diagrams because they're both examples of free body diagrams where my forces cancel out, giving me 0 net force. There's a name for that. If your forces cancel out to give you 0 net force, we say that these are balanced forces. Okay, they're balanced. This means that my net force is 0, and this means that these objects will not accelerate. Now, please don't misunderstand. Saying that the acceleration is 0 does not mean that these objects are at rest. They could be. I actually don't know. Both of these objects could either be at rest or they could be moving at a constant velocity. All I know is they're not accelerating. 0 acceleration doesn't mean 0 motion. It means constant motion or constantly at rest. Okay, it means there's no change in the motion. So if you need to make a note about that, you can. But 0 acceleration does not necessarily mean they're not moving. Okay, so again, these are balanced forces. If everything cancels out, we say they're balanced. There's also a name for the ones that don't cancel out. These 2 free body diagrams represent situations where you have unbalanced forces. When you have unbalanced forces, you will end up with a net force. It's some number value. For example, that one was 13 newtons to the right. It has a net force. And if there's a net force, there will be acceleration. And that acceleration will be in the same direction as the net force. So that one at the bottom left over there that says it has a net force of 13 newtons to the right, it's accelerating to the right. However, this brings us to a misconception. Again, just like the last one, I couldn't tell you if they were moving or at rest. With this one, I can't tell you which way they're going. Okay, let me show you what I mean. Here's those same 2. A free body diagram tells us the direction of acceleration, not the direction of motion. This object right here on the left, that object could be moving to the left and slowing down. Because if the acceleration is to the right and you're moving to the left, they're opposite, it would cause you to slow down. Or it could be moving to the right and speeding up. I don't know. The question would have to tell you which way it's moving. So when you look at a free body diagram, you do not know which way the object is moving. You only know which way it's accelerating, unless they label friction. If they label friction, your motion's opposite whatever friction is. Because friction always slows things down. It always goes against you when you're trying to move something. So if friction's labeled to the left, then you're going right. If friction's labeled to the right, you're going left. Okay, but if friction's not labeled, then I don't know which way these things are going. Same thing with this one. This one that says tension. I know that the tension is to the left, so I know it's accelerating to the left, but that doesn't mean it's moving to the left. It could be moving to the left and speeding up. That's fair. Or it could be moving to the right and slowing down. Think of it like this. This could be somebody pulling a wagon. Maybe they pull it from rest, in which case it would be speeding up and going left. Or it could be that somebody's dog got loose and started running to the right, and you catch up and you grab the leash and pull to the left, like that shows, to try to slow the dog down. Okay, so the direction of the net force and the direction of the acceleration is not necessarily the direction the object is moving. We looked at that before when we looked at all those graphs, and we said, hey, just because it says it's in a positive acceleration, it doesn't mean that it's moving in the positive direction, and it doesn't mean that it's speeding up. Okay, so again, these free body diagrams tell us the direction of acceleration, not the direction of the motion of the object. All right, questions about that? That is a common misconception. Okay. All right, let's look at one more example. I think this is the last one. This one we're going to solve for mass instead, so it's a little bit different than the other calculations. It says the forces acting on a toy car are shown in the free body diagram above. If the car experiences an acceleration of 12 meters per second squared, what is its mass? So this one's also different because they didn't give us the force in the question. They gave us a free body diagram that we have to use to get the force. The only number in the question is the acceleration, 12 meters per second squared. The net force isn't written in the question, but it is in the diagram. If I have 7 newtons of force to the left and 16 newtons of force to the right, what is my net force? 9 newtons to the right, right? Positive 9. Okay, so my net force is in that diagram. You just have to read the diagram to get it. So F net is positive 9, which, by the way, means my acceleration is positive 12. Okay, it will be in the same direction as that net force. All right, my unknown is mass. My equation is still F net equals ma. Substituting in looks like this. I have appropriate units already, but again, you should double check. If I want to solve for m, I need to divide both sides by 12. 9 divided by 12 is 0.75, and when I use this equation to solve for mass, the mass that you get will be in kilograms. That's the standard unit. Okay, so this is 0.75 kilograms. Are there any questions about this calculation? No? Okay. All right, then that's it for today's notes. For the rest of the period, you can use the class time you have left to work on 202.3 Newton's second law problem set. You guys have 20 minutes, actually 21, pretty much like my last class. So you should be able to get this finished in class, most likely, but if not, you can finish it for homework. You also have your RA. If you want to work on that, you can. However, you will have class time on Monday. So I would encourage you to work on today's assignment first. If you finish it early, you're welcome to work on the RA. If you have questions, please let me know.